Hello, this is Michael Denon, Vice Provost for Teaching and Learning and Dean of the Division of Undergraduate Education here at UC Irvine. And this is Conversations with the Vice Provost. This is where I take issues of interest to the undergraduates here at UCI, the whole UCI community. I like to say Orange County, California, and even the world. And I discuss them with colleagues from around campus and the community. And today's episode is particularly near and dear to my heart. I've got the Dean of Physical Sciences, fellow physicist James Bullock here. James, welcome.
This is going to be great, Michael. Thank you so much for having me.
So I'm going to start off, James, by telling you something you may not actually know about me. Okay. So as James knows, I'm what we call in physics, the technical term is an experimental condensed matter physicist, even more specific, experimental soft condensed matter. So I like to study foams, biological systems, other things like that. But I have a deep and long-standing relationship with cosmology. So as an undergraduate, I drove a microwave background radiation telescope from Princeton University to Saskatoon, Saskatchewan, Canada. That was one of the things I did as an undergraduate in December, James. So we were riding ahead of a blizzard. It was me and one grad student. That was my first sort of science mission. And as people may or may not know, the Princeton group was very big in the microwave cosmic background radiation detection, first discoveries, very exciting place to be. Yep. Second, I have to brag in the podcast. I did my senior thesis with Jim Peebles, who recently won the Nobel Prize. And I actually did my senior thesis on inflationary models of the early universe. So that's my other connection to cosmology.
Yeah, got the serious pedigree there. He's
serious pedigree. I did my PhD work at Santa Barbara. Institute for Theoretical Physics, and a very, very strong quantum gravity cosmology group. And now I'm very proud to say I'm at UC Irvine with, I would argue, one of the best, if not the best, astrophysics cosmology groups in the world.
You know, we like to think that, Mike, and Michael, thanks for saying that. You know, the thing that's really special, I think, about the cosmology astrophysics group at UCI is that we talk so much with the particle physicists. So it's really a connection between the astronomers and the particle physicists and tackling questions like the nature of dark matter that's really fundamentally interdisciplinary in that way. That's something that I think UC Irvine does as well, or probably better than any place in the world. So we're very proud of that effort here.
Sure. No, I think it's great. I'm going to start us off. You said the word, I do a lot of public speaking on science, and two of the big questions I get are what's dark matter, what's dark energy, what are we doing about it, as if there was something we would do about it, what do we know about it? And as someone, I'm not as active in that area obviously anymore, but one of the things I find fascinating is we as physicists often cause ourselves a little bit of trouble with the names we come up with. And I point out dark matter actually was a very good name for that physics problem. I feel like dark energy was us getting a little too fancy with the naming, or a little too, it makes sense if you really understand it from the physics side, but the public hears it. And too often I think they're thinking of the dark side of the force, James, to be honest.
Yeah, it's, it's the kind of name that makes you kind of lean in and say, what's that all about? But it's not that revealing. It's a name for something that we're quite ignorant about, unfortunately. We know the universe is expanding, and that's something that actually is independent of dark energy. But the thing that is weird and that we've discovered over the last couple decades is that the universe is accelerating in its expansion. That is, it's getting faster and faster in its expansion rate. And that phenomena is basically what we call dark energy. And it's a weird thing, totally unexpected, and in fact, even weirder than dark matter.
So let's start with dark energy, because I think it's an interesting place for people to kind of understand a little bit that interplay between sort of what happens in the world of theory and what happens in the world of experiment. Yeah. And this is clearly, I think I followed the history well enough. This was something that really theory didn't foresee necessarily. In retrospect, you can see where it was in theory, but this was fundamentally a measurement that happened that then needed to be explained.
Yeah.
And now theorists are really working hard on it. Can you maybe comment on that dynamic a little bit?
So I can sort of, take a step back and think about how weird this phenomenon of dark energy is for a second. Yeah. So, if you take a ball and you throw it up in the air, the ball comes back down. And that's because gravity is attractive, and the ball is in fact slowing down its whole way up until it stops and then falls back down. So when theorists were first thinking about what the universe should be doing with time, you have this expansion. There's stuff in the universe that's got mass. And so you're expecting the universe to be slowing down and slowing down and slowing down. If there's enough mass, it'll even fall back on itself and collapse. And so astronomers went out and they started to measure how fast the universe was expanding long ago by looking far back in the distant universe, and how fast it's expanding now, and trying to measure that slowdown. And they found something weird. They found the ball, rather than slowing down, was actually speeding up. And the universe is actually speeding up in its expansion. And that's the weirdness of dark energy. Now, was it impossible to sort of deal with that theoretically? No, but it was incredibly unexpected. It turns out Einstein's equations can handle it. But what you have to do is stick something in the equations that has an energy density. Basically, you need the free space itself to have an energy density at a level that's just super weirdly low. That's was so unexpected by theorists that there were theorists, I remember when I was in grad school, who wouldn't even teach that possibility in class because they would just say, this is so ridiculous. Clearly the universe wasn't built this way. Let's just move on to the other solutions, to Einstein's equations. And it turns out that no, we actually had to study those other solutions because that's what the universe is really doing.
Yeah. And so now we're in a place, I think, where we've been working on it long enough. It's true to say that the possible options, we've at least been able to eliminate maybe some. Is that safe to say? And could you comment on, like, what are some of the top experiments people are looking to? Because I think that's a key thing people need to understand, right? There's always this interplay between theory and experiment. So as theorists kind of map out, okay, these are the things that could explain it. That also tells you, well, what's the next experiment you need to do to really decide that?
Right.
And are we kind of at that point already, or is that still in the future?
Well, over time, since the initial discovery, people have been sort of working harder and harder to try to track back and measure more precisely what the expansion rate of the universe has been over time. And, initially the kind of models that we were trying to test were things like, well, what you need to make the universe speed up in its expansion is some kind of energy density in empty space, energy density in the vacuum. But this actually might arise from another particle of nature that's sort of like the Higgs, that pervades all space, but just has a very different mass scale. In principle, something like that, that's generally called quintessence, could be driving this kind of dark energy phenomena. And if that's true, you expect its energy density to actually change a little bit with time in a way that perhaps could be measured. And the thing that's amazing is, over the last sort of couple decades, astronomical sky surveys have gone out and tried to sort of measure this phenomena. And the thing that seems to work better than anything else is this idea that the energy density is actually constant. And in fact, the model that works the best is called the cosmological constant. And this was actually a term that Einstein stuck into his own equations long ago to kind of prop the universe up and keep it from falling back in on itself. It turns out that term might very well be there at this weird value that's not changing with time. So that's kind of where we are now. But there are other surveys planned to try to measure this expansion rate ever more precisely. And what we really hope is to see something change. We hope to see a little bit of a change, just to have something to grab onto, to build theories around, that it's not just this cosmological constant thing, which is just a number that nobody ordered and we don't know, it's hard to know where it came from.
Yeah, no, that's good. Real quickly, one last question on this, and I want to talk just a little bit about dark matter and microwave background briefly, and then go to our global environment. Yep. People will have all heard about, like, the theory of everything and quantum mechanics and general relativity being merged. Is there also a effort, a thought, a group out there saying, okay, we don't understand it now, but really this is one of those other examples of where we don't have a really good quantum theory of gravity either. And so maybe if we were to get that would give us some insights. I know that's kind of kicking the can down the road, and it's not really a solution, but is that really discussed? Or
I think so. I think there are some people who think that the dark energy problem theoretically is really, we're not equipped theoretically to handle it right now, and it's sort of a problem for 4 generations in the future. because we just don't have the physics yet. We don't have quantum gravity. We don't have those expectations to understand the vacuum at this level. Now, not everybody is that pessimistic. There are people trying to work on it. But if we think about dark matter, maybe we could pivot a little bit to dark matter. Dark matter, we think, is a more tractable solution. It's not as weird as dark energy. We have field theories that we think we could think about new particles, et cetera. So if there's a problem for 100 years from now, that might be dark energy. If there's a problem for today, that might be dark matter.
Yeah, and that's a great segue, because I think dark matter is the one that I've always been intrigued as an outsider, as someone inside physics but outside cosmology. It's the one that is like, wow, it's really clear that there's more gravity there, right? Like, you just look at how the planets not the planets, it's the stars and the galaxies that, at this scale are moving, and it's easy to imagine that there's things that interact with gravity, but you can't see, right? Which, for our audience, to me, that's the simplest definition of dark matter. It interacts with gravity. You can see its effect through gravity, but it's not lighting up in anything in the electromagnetic spectrum. So it's not interacting that way. And so electromagnetically, it's neutral. Gravitationally, it's not. So now we can go figure out what that might be. As someone not working in the field, I'm like, oh, shouldn't that be an easy problem?
Exactly. I mean, I think that's right. And I think I think traditionally that's kind of the way most of us think about it. And that's the way we've thought about it from the very beginning. You have a particle that doesn't interact electromagnetically. That might seem really weird, a particle that, that doesn't do that. And maybe it's worth pausing to explain that is a little bit weird. Like, for example, as you and I know, the reason why we don't fall through the floor and fall to the center of the earth is electromagnetism. The electrons in our shoes are pushing against the electron, or repelled by the electrons on the floor, and that's why we don't go through the floor. If you throw a ball at the wall, the same thing, it's electromagnetism. If you had a dark matter ball going at the wall, it would go right through the wall. And that's weird. But that's because it only interacts via gravity, as far as we know, and not the electromagnetic force. And so for a lot of time, people have been thinking about, okay, here's a particle that doesn't interact electromagnetically. Therefore, it's going to be hard to find and hard to touch and hard to control because it doesn't have a charge. But it could interact weakly with the weak force, which makes it hard to find, like a neutrino. Right. And here at UCI, we love talking about neutrinos because Fred Reines discovered neutrinos, and we're used to looking for things that are hard to find that way. But a new idea in dark matter that actually there's a lot of work going on in our school in the physics department, is ideas that there perhaps is an entire sector of dark matter phenomenology where the dark matter doesn't interact with our matter very much, but there's many different kinds of dark matter perhaps that interact with themselves. Now, this might seem crazy at first, but I like to think about it this way. Something like 1/6 of the matter in the universe is normal stuff. That's us. And the 5/6 is dark matter. We kind of know that's true. Now, that 1/6 of the dark matter is all of the periodic table, all of the standard model of particle physics, quarks and gluons and all that kind of interactions, right? That's the 1/6 of the universe. So a lot of people are thinking, now, wait a second, does it make sense that the 5/6, all the rest of the universe is just one particle that doesn't do anything and only interacts with gravity? Or maybe there's a whole sea out there of dark stuff that's doing things and interacting with itself. And that's a new idea that's emerged, and it's created a lot of fun things to think about in cosmology and galaxy formation, et cetera.
Oh, that's really cool. So on that, making our last transition, right, it's fascinated me always that the microwave background radiation is this remnant that we're allowed to use in a way that we can really look at the past because of the ways things interact with each other, right? Like, I don't know that people realize that these decouplings occurred at different stages in the evolution. So you get these fingerprints, and it's like a huge, amazing, wonderful cosmological scale detective story.
It really is.
And there's a lot we've learned from there. So maybe my question is, like, probably give a little context, but what is that next thing we're hoping to learn from the microwave background radiation?
Yeah, so I mean, as you say, the microwave background is this tremendous way that we can test and learn about the early universe. We have to understand the way particles are interacting at incredibly high temperatures and high densities very, very well not too long after the Big Bang in order to make predictions about what the cosmic microwave background should look like. And if you change little things like how much dark matter there is or how much normal matter there is in the universe, you will change what the cosmic microwave background looks like in terms of its structure. And so that's what allows us to measure it and learn this stuff. Like the cosmic microwave background is telling us there's got to be dark matter. There's got to be something that makes the universe sort of flat and explain that, we interpret that as dark energy in terms of its geometry, et cetera. So that's kind of what we've learned. We've learned a lot about what the conditions of the early universe were like and what the structure that sort of seeded the universe was that grew into what we see today. And the question is, what can we learn next from it? One of the things we're really hoping to do with the next generation of cosmic microwave background experiments is to measure the polarization of the light that's coming in very precisely. And it turns out that if we can do that, there might be a way for us to learn something about the very, very early times, the inflation that you studied with Jim Peebles a long time ago, right? The energy scale of inflation in principle could be tested by measuring those things. So we're talking about learning about physics that drove the universe 10 to the minus 40 seconds after the Big Bang. Or even if there was a Big Bang, or what the conditions were like at these incredibly early times, with energy scales that are so high, you would need a particle accelerator the size of the solar system to even come close to it. So it's an amazing thing that we can learn about the earliest microseconds of the universe if we can start making those kind of measurements.
No, that's really cool. Now we go from this grand scale and we go to the next grand scale, something kind of close to, I think, all of our hearts, behavior of the climate on the Earth. Or, yes, just the Earth in general. And my other little hat is I described myself as an experimental soft condensed matter physicist. I also do most things that are non-equilibrium and nonlinear, complex systems. And, there's no more complex system that we study immediately than the climate. So this is much closer to what I actually now do in my lab. But it's something UCI, again, we're just at the top of this area. We have our entire department of our system science. The founders of this are giants in the field. Maybe just comment a little bit from the school perspective, the role, but then I want to also talk about the university perspective, because as a campus, we're really all in on this.
We really are let's start with the school, but I don't want to forget about the campus. From the school, the building that my dean's office is in is called Rowland Hall, and that's named after Sherry Rowland, who discovered in that building on campus that CFCs deplete ozone. He did this with a postdoctoral researcher at the time, Mario Molina, and unfortunately he died very recently and had an op-ed in the New York Times about the story. But this is something we're really proud of at UCI, a discovery that happened here. And then Sherry Rowland and others basically dedicated tremendous time and energy to getting the word out about CFCs and how they deplete ozone. It eventually launched the Montreal Protocol, which ended with a worldwide effort to limit CFC production and the use of in aerosols, and eventually the ozone hole now is the smallest it's ever been measured. And so this is an example of scientific discovery and dedicated scientists, and then the world coming together to actually make a difference and change things. And that's a legacy that we have here in this school, and the campus should be proud of. And someone who knew Sherry Rowland, who was cited in that Nobel Prize winning work, was Ralph Cicerone. And we brought Ralph Cicerone here to start a brand new department, which was the first of its kind in the world, called the Department of Earth System Science, to study the Earth as a system in a very interdisciplinary way with atmospheric chemists, but also with glaciologists and engineers, physicists. We even have someone with a law degree in the department now. And it's this really amazing effort to think about the globe, the Earth as a system, as a physical system, but also how biology is affected, how humans' interactions affect the climate in a small DT way. And we are really dedicated to this question of not only figuring out what's happening with the climate and why, but then what things can we do to begin to sort of make a difference in terms of greenhouse gas emissions? What do we need to do in the energy sector to really move the needle on this problem? So it's
No,
very high
yeah,
priority.
very exciting. Something you mentioned about Sherry Rowland's story that I think is critical in this space, and we'll make sure we come back to the campus, but it's the communicating of this.
Yeah.
You and I both have actually various levels of experience out there communicating with the public about science. And in my areas, it's really interesting how quickly and early on in the process, I mean, I think no one would deny that climate science got a bit politicized, if not a lot politicized, right? Depending on your perspective. Um, and it's fascinating to me the challenge in this day and age of, how do we communicate this in a way that's meaningful
Yeah.
to the public? And obviously, Sherry's story is a great success story. That one worked. Climate change, I think we're turning the corner on it, but it had a challenge early on in its communication phase that just surprised me a little. But in retrospect, I think makes some sense because of things that were focused on. Perhaps it's always easy to be a Monday morning quarterback, as they say, in hindsight's 2020. But how do you see that as now that you're in a role as the dean, right? How do you see that communication effort? And that probably ties to the full campus effort as well. It's probably a natural connection.
Yeah. Well, I think it's non-trivial, Michael, as you say, and climate change is a harder problem than the CFC problem.
Right.
So there's a lot of different ways to think about it. I think in the early days, it's unfortunate that I think a lot of times, a lot of people probably heard of climate change for the first time from someone who was a politician.
Right.
And whether or not the politician was right and with the science, that's going to color your reading of it, right? And so I think the role of scientists in this is ever more important. And I also think that the role of scientists and sort of calling it like we see it in every aspect and is important too, because I think that we need to be seen as arbiters of the truth and science, and we have to sort of say, this is what we understand and this is what we don't understand, so that people trust us.
Right.
And so that's a piece of it. I think another piece of the communication too is I think some people are a little bit confused about what the incentive structure might be for a scientist.
Right.
Right. So
I'm with you on that.
Some people think, oh, well, there's a couple points that maybe it's not common for everyone to understand. Like, I get a big grant, okay? So I'm incentivized to get good grants by doing good science. I don't take that grant and buy myself a house or a boat with it. I take that grant and I pay graduate students, $35,000 a year to do research. That's what I'm doing with the grants, right? That's the vast majority of grant funding, is to pay PhD students very small amounts of money, unfortunately, for them to do research. We're not getting rich off these grants, right? And so it's not like we have personal motivation to enrich our own selves. We're motivated to get funding to do the research that we want to do. So that's one thing to kind of clarify, I think, when people think, oh, you're incentivized to say one thing or another. The other thing that we're incentivized to do is to make discoveries that transform the vision of the direction of the field, right? So like in my own subfield, if I could prove Einstein was wrong, I would do it. This is not a massive cover up, right? If I could do that, I would get a Nobel Prize and I would be very happy with that, right? If I could prove aliens were real, I would do that. I am not trying to hide that from you. If I could prove that, I'd be doing well. And it's sort of the same thing with climate. Like 99% of all climate scientists are just trying to do the science and get the right answer and tell you what the answer is.
Yeah. James, I just want to interrupt. I want to say,
go ahead.
It's exactly what I point out to people. We are the worst group to ever maintain a conspiracy, because it doing that hurts our own career. Like, our incentive structure is highly individualistic, not collective, And so if you are the one who had the absolute incontrovertible evidence that something else is true, you're going to shout it from the rooftop, because, as you said, that gets you the Nobel Prize, that gets you the next big grant. Right. And so this idea that scientists would collude in a conspiracy is always struck me as interesting, because it really shows that you don't really necessarily understand how we're incentivized.
Right. I think that's right. And so if we think about what we need to do as scientists when we talk about really important problems like climate change, I think one thing we can also do is to try to loudly, if we see things that are even on the sort of side of, this is what climate change is doing and this is what we should do to fix it. If there are errors with what should we do to fix it, we need to call that out and say, look, that's actually not the right thing. We really need to think about this thing. So let me just give you an example of that from the school perspective. There's been a lot of work that folks in our school have done looking at the energy sector and what it's going to take to tangibly move the needle on carbon emissions. And unfortunately, you will hear a lot of talk about electrification, that electrification is the answer. We're going to put solar panels everywhere. We're going to put batteries in every garage and everyone's going to drive a Tesla and then everything's going to be fine. That's not going to work. You can't make cement that way. You can't store that much energy in a battery from day to night, from season to season. We need to think of more effective ways to store that energy. I'm not saying that there's not a role for that. There's a very important role for that. But you have to explore other things in the energy sector to really move the needle. It's not going to be free, but in the long run, that investment is going to make a big difference. So for example, hydrogen energy storage is going to be very important. If fusion energy comes along, and there's a history in fusion energy at UCI, if that turns on, that's obviously going to be transformative and very important. But thinking about all of these things and be able to sort of say, look, it's great that you're talking about that, but actually, when you run the numbers, we really need to do it that plus many other things. I think we have to be truthful about those statements as well.
Yeah. One other thing which will tie in, I think, to the campus, James, that connected for me is the other conversation I've had with people. I feel like the needle's definitely moved from climate change versus no climate change to humans contributing to climate change to humans not. I slightly facetiously and slightly seriously say, I really hope that it's partly humans contributing to it, because if we've contributed to it, it makes it more likely we can mitigate it.
Yes. That's
either way, right? Either way, I think, like, just because it wasn't caused by human activity doesn't make it any less dangerous to humans' ability to live in the world. Like, we evolved in a world of a certain climate. And even if this was a natural swing to a warmer climate, it's a warmer climate we're not evolved to live in. And so the idea, you mentioned it, the idea of looking for solutions is so critical in my mind. Like, don't ignore the debate is what's causing it is obviously important, and the causes feed into the solutions. I get all that. But even with that sort of pushed a little bit to the side, solutions are something, I think, independent of the cause, you need solutions, right?
Yeah.
I think that's right. And I feel the public conversation has really moved to, we all agree it's happening. Now we're just worrying about the cause. Is that your read of the current situation?
So, and, I think even the current situation is there's more and more clarity that, if you just look at the isotope ratios of the carbon, it's clearly coming from burning fossil fuels, not a natural carbon, all that kind of stuff.
No, I would say from the science side, it's clear we're involved, James. I'm saying from the public opinion side, I think it's shifting.
Right. I think it's even in the public opinion side, it's beginning to shift. And it's certainly true that, right, even if you are sort of, for whatever reason, don't believe the scientists and don't think it's coming from burning fossil fuels, you still want to solve the problem because you don't want this to happen. It's been a long time since we had this much carbon dioxide in the atmosphere. And the last time we were in equilibrium, the sea level was 20 feet higher. Like, this is not normal. And human beings had not yet evolved. So, like, we are living, this is unprecedented for our species. Right. And then we think about solutions, but this is the thing that I think is crucial. I think there are solutions. This is not a hopeless situation. This is not, nothing we can, we can do something about this. And it's important to recognize and understand that. This isn't just about, I'm going to tell you more about how the polar bears are in trouble. I'm going to tell you more about how the sea level is rising. We also want to figure out what to do. Yeah. And there's a lot of things that people are working on. Energy that doesn't come from burning complex carbon. If you think about it, if we're using, 18th century technology to run our world, right? We're just digging stuff out of the ground and burning it. That's what we're doing to get heat and make an energy with that. And it's amazing how good we are at it. The infrastructure that we've built to move oil around the world is incredible. It's incredible how cheap gasoline is. It's amazing that we can do it. but we gotta switch. And I think if we do switch, it can be so much better. So that's another thing. And when we talk about building new materials, we're going to start talking about quantum soon, right? Imagine we just had windows that were collecting solar energy all the time to sort of heat homes. Imagine we could build materials that were incredibly energy efficient, that were superconducting, that didn't waste energy all the time. That's a way of thinking about things. There's ways we can think about moving to a different way of living our lives that can be a lot more efficient, cleaner, and in fact, in the long run, create the kind of jobs that people would want to have. People would rather work, in a fusion reactor, which is clean and crystal, than digging up coal or even on an oil rig. This is lifestyle that I'm not saying we could turn it on a dime, but this is a place we can begin to move as a society that could really help everybody, and it's driven by technology.
Yeah, no, that's amazing. And I think real quickly before we talk quantum, on our campus, that's what's so great about UCI is we're not just thinking about climate change in the physical science department. It's a campus-wide effort, because I think it's going to take the social sciences, the humanities, the arts, to really both be creative about the solutions and to make sure society is excited about adopting them.
I 100% agree. One of the things we've been doing is there's a group of us who've been meeting that were called Solutions That Scale. And the idea is to create solutions that will scale globally for this problem, fundamentally based on physical sciences, but also involving computer science, engineering, social ecology. But we have ongoing conversations with the law school, the business school. We need to engage with business leaders and the community about how do we do this in a way that makes sense for the economy and for the world. This is a place, and of course the humanities are so essential because they're going to help us tell this story and communicate why it's so important. And every dean on campus, whenever we talk about this, talk about climate change, everybody sort of says, yeah, we got to collaborate on this, and I really believe it. This school, this thing about being rated the coolest school for so many years in a row by Sierra Magazine, I think it's important for listeners to understand that this is not just some writer making up a top 10 list like you might get in some magazines. Though there's serious criteria into this, and this campus has done the first of its kind electrification bus fleet. We have more incredibly efficient buildings on this campus than any campus in the country. We have our power plant. We have a certified microgrid where we can do things like use hydrogen to store excess energy and actually in real time, walk the walk on these issues. So, and there's something like 460,000 sensors on laboratories all over campus that are constantly monitoring things so that we can turn off the air conditioning if we need to. You're talking about factors of several efficiency that we gain just running the campus. So it's incredible what we're doing as a campus in that direction. And I think really a model, to the world for what we can do.
No, I'm glad you mentioned that, James. It's awesome that we both live it. We have everybody working together to make it out to the world, and we research it. Like, that's what a public research university should be about. The whole areas. So real quickly, in our little bit of remaining time, I'll make my little joke. We'll go small. We'll go to quantum mechanics. And I wish I could remember, I'm going to apologize to one of our colleagues at another university who I saw say this once, just because quantum mechanics is confusing doesn't mean it explains everything in the world that is confusing. But it certainly does get quoted a lot to try and explain everything. And as a huge science fiction buff, it is clear that both quantum computing and nanotechnology are the two things that, for whatever reason, science fiction movies think will either take over the world and kill us or save us, right? Unclear what it's going to do. But I think the other thing I think is hard to explain, but I'm proud of for people, we're shockingly ahead in the world when it comes to really what I would call contemporary quantum physics, right? Yeah. Which is an interesting thing to say, because if you're in the know, you can almost feel like, oh, quantum, that's done, right? People figured it out. The only real problem is getting quantum mechanics and gravity to work together. But quantum mechanics itself is kind of a solved problem, right? When in fact, there's a ton of interesting questions. And it's also got amazing applications left to give to the world. And some of the biggest applications that we use every day, whether it's the core of our computers, the core of lasers, the core of MRI technology, like most of the really cool technology we use, I think is because we understood and manipulated elements of the quantum level and realm. So what is like that next frontier, James?
Yeah.
What is, and what are our school doing that people are going to be shocked by?
Well, I'll start with a couple of things. Since you were talking about technology and sort of working towards it, take for example electronics. As you know, electronics are governed by manipulating electrons, and so you have to understand the quantum world to understand how to make a transistor and these kind of things, right? So that's certainly true. But electrons have something else besides charge. They also have a characteristic called spin, and that's a more subtle thing that associated with the quantum angular momentum. But one of the things we're working really hard on in this school is using spin as the element of, say, in electronics. So it's called spintronics. And you can imagine by using spin, manipulate things, next generation hard drives that just can store, hundreds of thousands of times more information with much less energy use. Similarly, doing computing with spins would be incredibly energy efficient, and again, not take this huge drain on doing computing. So that's just a kind of thing that people are doing. But I think maybe even more exciting if we sort of extrapolate into the future and we think about the quantum realm. As you know, quantum mechanics governs the structure of matter, right? If you want to understand what happens when you put some atoms together to make a molecule, that's quantum mechanics. And the problem is, even if you can write down the equation, you can't solve them. Solving these equations for like even a small molecule directly is really, really, really hard. There's people who just spend their life, and we have some of the best quantum simulators in the world here at UCI. But one of the dreams is if we get a quantum computer, right? So quantum computers that are using quantum qubits as instead of bits, in principle, these computers can be incredibly fast. But one of the things you don't hear a lot about is what are we actually going to use the quantum computer to do? Because it's not clear what kind of problems it'll be good at solving. The one thing that everyone is almost certain about is that quantum computers will be really, really good at solving quantum problems. For example, understanding what's going to happen when you put a bunch of atoms together, how are they going to behave? What's that material going to be like? And so I like to call that quantum design. So I can envision a future where when we have quantum computers, what are we going to do with them? And I think what we're going to do with them is we're going to design quantum things. We're going to design new materials from first principles on the computer without needing a laboratory, right? And so we can really get way ahead of things like, oh, if we look if we do this and we twiddle these knobs and I run my simulation, boom, it's superconducting at room temperature at atmospheric pressure. If we could do that, right, that's fantastic. So then you have superconducting stuff that you can utilize all over the place. Yeah. Just imagine if you could quantum design robots that would go in the human body and seek out cancer or cure disease. I mean, the future of quantum design in principle, if you could really manipulate the quantum world from first principles, is kind of limitless. And so, yeah, that's way in the future, but I don't think it's impossible. And I think that that's a vision that a lot of us share, that if you think about, what's the future of technology, it's going to be an understanding how to manipulate things on the quantum scale to do what we want them to do.
James, that's very near and dear to my heart at the non-quantum scale, of materials. Because as I mentioned, I do experimental soft condensed matter. So I study bubbles and foams. And you'd be like, well, why do you study bubbles and foams? And a lot of the material science design happens now at that scale that we can handle, which is, at the scale maybe of microstructures or even macrostructures, in my case of bubbles manipulating foams, because we can't do what you just said, the quantum design yet, right? We can sort of do the classical design. And a lot of what I see in this evolution of materials, humans were very, very creative to figure out things like steel when we did, like alloys. But that was all done kind of experimentally, trial and error.
Trial and error.
We're all familiar with the story of, Damascus steel. How did they make it, right? That was brilliant, but we lost that in principle. Now we can actually go back and measure it and get a better idea of how it was made. But now we design sort of by empirical principles that we've built up over time. And I think you're right. Like, for those who may not be aware, a lot of our new, whether it's drug discovery or materials, is experimentalists doing a lot of labor, using clever ideas, clever understandings, but they still have to try a lot of things to get the right one. And what we're really talking about is, we know the fundamental theory, as you said, is quantum mechanics. We just don't have the computing power to solve it. And this is going to give it to us, which, like I said, I just had to repeat that because it's so exciting to me, because what I do is deal with material design.
Yeah. I mean, it's hard, you know, and right now I want to emphasize that again, it's a lot of trial and error and a lot of intuition. You know, I mean, I have so much respect for folks like you who have that intuition. I don't know where you get it, why you started with this and felt like you needed to add this to it. And suddenly it's, you know, I don't understand where that comes from, but it's almost black magic-y or something. You know, you've got this intuition that you develop over years and years. And I think this vision is ultimately, we might actually be able to do these things from first principles. And boy, that's going to change. That's going to be a game changer.
And it closes our loop with climate change. As you said, these are the materials exactly that we need. I think this is a great point to wrap up, James. This has been so much fun. I could talk about this for hours, but
me too.
I know people probably only have a 30-minute commute, and that's what they're using to listen to the podcast. So we want to keep it to those timelines. But James, I hope people understand not only the excitement of the science you and I talked about, but the excitement of UCI in this space. Because I know I'm a little biased. I'm from the school, both UCI and the actual School of Physical Science and the department. But it's an amazing place. There's amazing things happening, and people should come check us out and find out what we're doing. And thank you so much for your time. I think this has been a great conversation.
Thank you too. This has been great.
And to our listeners, thanks for checking in and listening. Come back for more podcasts. We'll see you soon.